Hi, we are Team 6, and our master's project was investigating the efficient energy management of commercial buildings with energy storage systems. The motivation for this project is the large environmental impact of commercial buildings, which is driven by their increasing energy consumption. The primary aim of this project is thus to reduce the energy consumption and cost of a commercial building while maintaining the service level for its occupants. To do so, the team modeled a UK fire station, with both a physical benchtop demonstrator and building modeling software. It also developed a data acquisition system to use sensors to aid the modeling of the building's internal behaviors. The team then used a decision-making algorithm and various static improvements, such as an energy storage system, to make a set of recommendations to the client. These recommendations were thoroughly tested in a MATLAB simulation and successfully delivered upon the project's aim.
As a key part of this project, a benchtop demonstrator was designed, built and tested. This image shows the design of the model, and it is comprised of 50 individual sections and is scaled at 1/12 the size of a fire station in Nottinghamshire. The model was thermally insulated with a heating system which aimed to increase the temperature within the model by 5 degrees Celsius. The heating circuit was built with temperature sensors which could monitor the temperature of each room and display the results live, such as this. Many thermal tests were run on the building which enabled thermal models within the decision-making algorithm to be validated. In addition to the thermal characteristics of the building, a scaled load circuit was also installed. This comprised of a load resistor which represented each of the main loads within a commercial building, and an LED which displayed whether the load was in use. The loads were scaled to 1 to 35,000th of real building loads. The model can then be used for a physical demonstration of the final system to key stakeholders, as well as validation of further results.
A sensor system was developed allowing the measurement of indoor building parameters such as temperature, humidity, and CO2. Collected data was successfully used to provide an estimate of typical room occupancy schedules for a variety of room types. This data was integrated with the algorithm, allowing for a more effective load optimization. The system was designed with a focus on simplicity for the end user, with features such as wireless communication. Two thermal building models were created for the simulation of room temperatures. These models take in inputs such as heating sources, building dimensions, and material properties. A more simple building model was created using MATLAB and Simulink, which was used for prototyping the decision-making algorithm. The final algorithm used a more detailed model, which was created using Energy Plus software. Validation work was completed using the benchtop demonstrator to assess the accuracy of the simulations to physically collected data.
Our dynamic and static improvements seek to reduce energy consumption and cost while maintaining the service level for the building. The dynamic improvements were an occupancy-based light controller in the building and a decision-making algorithm. This algorithm controlled a local grid of the building, a large battery, renewable power sources, and the grid, and successfully managed to reduce the cost and consumption of the building.
At the end of the project, we have successfully modeled a fire station, both in software and as a working benchtop demonstrator. This was based on data from our clients, academic sources, and our own sensors. Using the results from our extensive testing, we configured the decision-making algorithm, the indoor lighting control, the large battery, and the renewable power generation to reduce the building's consumption and cost, all while maintaining the service level. Specifically, our recommendations decreased the building's load by 21% and the energy consumption of the whole building by 8%, all with a yearly cost of £1,750. Therefore, we have successfully achieved our project's aim.